Hello everyone, I'm Tony from Intel. Today I will give a talk with the topic From Correctable Memory Errors to Uncorrectable Memory Errors. What error bits tell? This is the joint work with Yu Zhang, Jialei Wang, Hang Chen, Xian Liu, Tai Huang, Liang Peng, Shen Zhou, Lixin Wang, and Shi Jienge from Intel and ByteDance. If you see this video, then it means that I cannot present in person in the conference due to the strict COVID-19 policy in China. Well, in China, it is debated, most likely in a useless manner, on whether we are overprotecting ourselves from the virus or not. Similarly, someone may wonder whether we are overprotecting DRAM from errors with the strong chip kill error correction code, consuming many ECC metadata bits. However, some of us may not know that at some time in the past, Intel made the decision to use a weakened ECC on the contemporary server architectures with less ECC metadata bits. Today, I'm presenting a large-scale field study trying to understand the impact of the weakened ECC. Here is the outline of my talk. First, we will briefly introduce the background on DRAM reliability and error correction. Next, we will describe the large-scale field data from ByteDance in the high level, and explain why the dataset is unique. After that, we will propose a new indicator, the risky correctable error indicator, for the analysis using the dataset. Then we will go one step further to see how the new risky C indicator can help uncorrectable error prediction. Finally, we will give the concluding remarks and the future outlook. A dual inline memory module is composed of many DRAM chips. Each DRAM chip has several banks. Each bank is a two-dimensional array indexed with the row and the column. During a memory access, each DRAM chip provides a set of bits from the same bank, row, and column to form a catch line. Given a bank, row, and column from an individual DRAM chip, the set of bits are served through m data pins over m bits or bursts. If there are certain faults in the micro-level DRAM circuits, for example, in a row, then the memory access on the faulty row will result in a catch line with errors. Note that the errors may be uncertain. For example, given the right data with ones and zeros, if the faulty row is full of stuck-at bits of 0, then no matter whether the data bits of 0 or 1s are written, a read operation will always result in 0. Note that only those data bits of 1 will become erroneous. Such errors are uncertain without knowing the right data content. The catch line is fed into the error correction code for error detection and correction. If the error is within the ECC's error correction capability, it becomes a correctable error. If the error goes beyond the ECC's error correction capability, it becomes an uncorrectable error, leading to a system crash by default, or to an application crash if some advanced RAS features are enabled. Traditionally, the chip kill ECC is enabled on server platforms. Its name implies that it can tolerate any erroneous bits from an individual chip during a memory access. However, with the current generation of Intel server architecture, the ECC gets weakened. Some ECC metadata bits are repurposed for other uses. There are less than enough number of ECC metadata bits to tolerate all the possible erroneous bits from an individual chip. The unfortunate part is, to the best of our knowledge, the impact from the weakened ECC has not been studied in the past literature. So today, we present the first attempt to study the impact using the large-scale field data from ByteDance. This is the server farm of ByteDance containing around 100,000 servers with Intel Skylake and Cascade Lake architecture. That is, the most recent ones. The servers are with DDR4 DIMMs from Samsung, Hynix, and Micron, the top 3 DIMM manufacturers. The data collection spans for 8 months. We have observed CEs on around 10,000 DIMMs. Among them, more than 500 DIMMs experienced UEs later. The dataset is unique in terms of 2 attributes. We have erroneous bits for all the CEs. We also have the DIMM part numbers, that is, modules of DIMMs available. Actually, for each of the 3 DIMM manufacturers, we have more than 10 unique part numbers of DIMMs with errors. Attempting to understand the impact of the weakened ECC, we first define a new concept, risky CE. For the weakened ECC on Intel architecture, the details are highly confidential and are never exposed. Even for me, an insider from Intel do not know. However, there is certain coarse-grained ECC knowledge available, which can be provided to major customers and partners upon request. Those are some well-defined fully correctable error bit patterns. If the erroneous bits of an error from an individual chip can be covered by one of the patterns, then the error is guaranteed to be correctable. If the bits cannot be covered by any patterns, then occasionally the error is uncorrectable. Given the fully correctable error bit patterns, we define the concept of risky CE for analysis. A risky CE is a CE with its erroneous bits not covered by any patterns. Note that even if the bits are not covered by any patterns, it is still a correctable error. Here we illustrate further with some concrete examples. We take 2 examples for fully correctable patterns from a publicly available paper. Note that the 2 patterns are not for the Skylake or Cascade Lake architecture, but for the future Intel architecture for DDR5. In the first pattern, if the erroneous bits are bounded in the left half of the set of bits from a chip, then the error is guaranteed to be correctable. In the second pattern, if the erroneous bits are bounded in the right half, the error is also guaranteed to be correctable. Assuming that there are only 2 such fully correctable patterns in total, as are shown on the left side. Now on the right side, in the first CE example, given its erroneous bits covered by the first pattern, this CE is not considered to be risky. In the second CE example, given its erroneous bits covered by the second pattern, it is also not risky. Now for the third CE example, the CE is risky, since its erroneous bits cannot be covered by the 2 patterns. Now we examine the risky CEs in the field data. We divided the DIMMs with errors from manufacturer A into 2 populations, one for DIMMs with CEs only, and the other for DIMMs also with UEs. We then plot the cumulative distribution functions of the risky CE numbers for the 2 populations. As we can see from the CDFs for DIMMs from manufacturer A, for most DIMMs with CEs only, the risky CE number is 0. In contrast, for most DIMMs also with UEs, the risky CE number is not 0. For comparison, we also look into the most commonly used metrics, the CE rate. As we can see from the right side, the CDFs of the CE rate from the 2 populations are much less discriminative at any thresholds. This indicates that in most cases, one risky CE discriminates the 2 populations. The observation is similar on DIMMs from the other 2 manufacturers. We then propose a new risky CE indicator for DIM. This indicator gets activated after observing a risky CE on the DIM. The rationale of defining such a new risky CE indicator is that the coarse-grained fully correctable patterns provide the adequate ambiguity to identify some risky but correctable errors. We conjecture that the uncertainties of the errors caused by the same fault then plays a role in correlating those CEs to a potential UE in the future. We expect that the new indicator is useful in analyzing future UEs. We first verify our expectation with a simple test. We use the new risky CE indicator in the test of future UEs for DIM, similar to the PCR test of COVID-19 for a person. We use the most commonly metrics, sensitivity and specificity, in evaluation. We see that the new risky CE indicator is both sensitive and specific in the test on DIMs across all the three manufacturers. In comparison, using the CE rate with different thresholds cannot achieve both the high sensitivity and the specificity. This indicates that the new risky CE indicator is highly correlated with future UEs. From the high correlation, we then conjecture that the weakened ECC contributes substantially to many UEs today. We then go one step further, that is, to use the risky CE indicator in UE prediction. The problem setting is to predict whether a DIM will experience future UEs given the past CE history of the server. In this problem, we evaluate the performance with the metrics of precision, recall, and cost reduction in proactive DIM replacement based on a simple cost model with different ratios of UE cost, DIM replacement cost, and workload migration cost. We start from the straightforward use of the indicator, and then extend to the more sophisticated approach based on micro-level DRAM circuit faults and the DIM part numbers. The straightforward use of the indicator is to predict that a UE will occur on DIM if its risky CE indicator gets activated. Here we show the precision and recall for UE prediction on DIMs from different manufacturers. For comparison, we take the most commonly used baseline, CE rate with different thresholds. As we can see from the figure, the new indicator is much more precise than the best performing CE rate baseline with comparable recall values. However, on DIMs from manufacturer C, the absolute precision is too low to be practically useful in terms of reducing the total cost with proactive DIM replacement. To improve the cases in which the precision is not satisfactory, we resort to a more sophisticated approach using rules. The approach is inspired from some previous work that UEs are correlated with certain faults in the micro-level DRAM circuits. A rule is applicable to DIMs from a certain manufacturer with its format shown in this slide. In addition to the risky CE indicator in the precondition, we allow for two optional components. We may include an optional micro-level DRAM component fault, that is, row fault, column fault, or bank fault. Those faults are identified with certain conditions specified by some parameters. With the fault indicator as part of the precondition, the rule can associate future UEs with certain micro-level circuit issues. We may also include an optional precondition of a DIM part number. That means the UE-prone fault is specific to the part number only. Without the part number in the precondition, it means that the UE-prone fault can be generalized across different part numbers from the same DIM manufacturer. we propose to learn a decision list of rules with the risky C indicator. This is done through an iterative induction of the most confident rule from the remaining data at hand. In each iteration, we enumerate all the possible preconditions and find the most confident rule. To score the confidence, we assume that for all the data satisfying the precondition, whether UE occurs or not follows a binomial distribution. Then we are able to estimate the lower bound of the 95% confidence interval from the empirical sample. Since less data usually results in a wider confidence interval in estimation, this helps penalize the preconditions applicable to only a small number of samples in the confidence scoring. After the most confident rule is identified, any data covered by its precondition are ruled out. The remaining data goes to the next iteration. The principles of such a learning approach are to always keep the rules learned confident to ensure the precision descent, and at the same time to obtain as many confident rules as possible to gradually improve the recall. In practice, usually there are not many confident rules exist. This means that only a few UE-prone faults are available. This list gets induced quickly in several iterations. Now we show the prediction results of the decision list with the sophisticated rules learned. In evaluating decision lists learned, we use tenfold cross-validation. With cross-validation, we make the training data and the test data exclusive. Meanwhile, we also make sure that each DIM with errors is used in prediction once and only once, so that the results are comparable. Comparing with the straightforward use of the risky C indicator only, we now improve the precision significantly for DIMs from manufacturer B and C with the moderate degree on recall. With the precision and recall balanced, we achieve a better cost reduction in proactive DIM replacement, even in the most challenging scenario with low UE cost to DIM replacement cost ratio. This results in a practically useful solution. We then compare the new approach with some other baselines. RWU boost is the boosting approach for imbalanced dataset using the micro-level fault indicators, but not error bit information or part number information. The other two decision list baselines are derived from the new approach for ablation study. Different from our new approach, the fault-only decision list does not use the risky C indicator. The error bit number decision list uses a different type of indicator, comparing either the average error bit number or the maximum error bit number against a certain threshold. From the results, we see that the other baselines that are not using the new risky C indicators underperforms. The precision is either lower with a comparable recall or much lower if the recall is relatively higher. Comparing with the proposed approach, the baselines are also not favorable in terms of cost reduction in proactive DIM replacement. This demonstrates that using the new indicator results in the state-of-the-art performance in practical UE prediction. We also performed further analysis based on the field data and the predictors learned. First, we show that we may vary the confidence threshold in iterative rule induction. With a higher threshold, we will learn less but more confident rules. This trades the higher precision with a lower recall. We also show that the new risky C indicator plays a vital role in UE prediction. In some cases, the most precise prediction is achieved when it is combined with a certain micro-level fault indicator and a certain DIM part number. The UE-prone faults identified exhibit different characteristics on DIMs from different manufacturers. Sometimes a UE-prone fault can be specific to a certain part number. In some other cases, a UE-prone fault can be generalized across different part numbers from a certain DIMM manufacturer. More details about the further analysis can be found in our paper. To conclude, we have presented a study on the large-scale field data from ByteDance. We have proposed a new risk KC indicator for a DIMM based on coarse-grained ECC knowledge. We have demonstrated that the indicator is highly correlated with the future UEs on the DIMMs, leading us to conjecture that the weakened ECC contributes substantially to many UEs today. We have also employed the risk KC indicator in UE prediction. Combining the indicator with micro-level circuit fault indicators and DIMM part numbers, we have obtained practically useful UE predictors, achieving state-of-the-art performance. We are transitioning to the new DDR5 era in near future, maybe slowly. We will see many new different factors. For example, there are some cost-reducing DDR5 DIMMs by saving a DRAM chip, then with much less ECC metadata bits. We will have the on-die ECC correcting one bit, but may miss correcting other bits if there are more than one erroneous bits. We expect to co-design the ECC and the DIMM architecture with bounded faults. Also, at the beginning of the new era, we will probably have the less mature memory controllers. The risk KC indicator will still be applicable if we have well-defined fully correctable patterns. If we could design the ECC and the DIMM architecture based on those patterns, we hope that there may be less risk KCs, and therefore less UEs impacted by the weakened ECC. However, we do not know until we see what happens in the field. At that time, we may need another analysis with certain field data to tell whether we are overprotecting or underprotecting. So that's the end of my talk. Any questions or comments are welcome. Thank you.